Well, thank you for the invitation. It's great to be back. I was a postdoc here. 3 years ago.
Yeah, so he was the ones using these postdocs that I mentioned from Gustavo and University of Miami before INSA existed.
Experimental postdoc. It's much of fun. So I'll talk about homotopy theories of coalgebras. So let me start with a general question. So motivating questions in algebraic topology often take the following form. So suppose we have a given functorial invariant f. So this notation means f is a functor from the category of topological spaces, equipped with a specified notion of weak equivalence to some other category C, also equipped with a notion of equivalence. And when I write this notation, I suppose that f preserves this notion of weak equivalence. Right? So often in algebraic topology, one encounters a functorial invariant that preserves a specified notion of equivalence. And we ask, how much does this invariant know about a space considered up to that specified notion of weak equivalence? Right? Or can we recover X functorially from f of x? Usually C is some sort of category that unlocks some effective analysis about qualitative or quantitative properties of the space, right? Usually C is the objects of C have some combinatorial structure or some algebraic structure. And the answer to this question often involves constructing an adjoint in a homotopical sense. An adjoint that also preserves these notions of weak equivalence and comparing the adjoints applied to that functorial invariant and your original space. How far are they from being equivalent? That's a central question in algebraic topology. And as I said, F usually unlocks some effective analysis, computational wise or conceptual wise about the topological or geometric properties of space. And today, our category C will be some version of coalgebras, co-associative coalgebras over a ring R. F, which will be a left adjoint, will be a version of the chains functor on the space. And we will consider different notions of weak equivalences on coalgebras and compare the resulting homotopy theories that we obtain and describe their meaning. So let me start with some history. Where has this question been explored, in what context? So the first context is rational homotopy theory of Quillen and Sullivan. So this is Quillen's formulation of rational homotopy theory. So Quillen considered simply connected simplicial sets. That's what this superscript means. Under rational equivalence, rational homotopy equivalence. So a map of simplicial sets is a rational homotopy equivalence of simply connected simplicial sets. If it induces an isomorphism on rationalized homotopy, right? Or equivalently, if it induces an isomorphism of rational homology. And Quillen constructed a version of the chains functor that associated to any simplicial set produces a differential graded co-commutative coalgebra over the rational, which is simply connected. I'll explain what that means in a second. It means that degree 1 is trivial. Consider under quasi-isomorphism. A map of coalgebra of differential graded coalgebras is a quasi-isomorphism if it induces an isomorphism on homology. Right? And Quillen proved that this version of the chains functor is an equivalence of homotopy theories in an appropriate sense. Okay. He used the framework of model category theory to make this statement precise. And there's a third category as well that fits into this equivalence, which is differential graded connected Lie algebra over the rational, also considered up to quasi-isomorphism. And Quillen proved that these three homotopy theories essentially contain the same information. Sullivan gave another version of this theory in terms of differential graded commutative algebra for spaces of finite type. Okay. And also developed a theory of minimum model, namely described a way of extracting the simplest model for the cochain and did explicit computations with that. So later on, people wondered what can one say over fields of characteristic P. So this is known as p-adic homotopy theory. So this was work done by Igor Kriz and Paul Goerss in '95. And the version I'm describing here is a formulation due to Goerss. And I'm going to be a bit more precise here because this is what I want to build upon today. Okay, so Goerss proved the following. So for any field F of arbitrary characteristic, one may consider the functor of simplicial chains. So this SC coalg means simplicial co-commutative coalgebras over F. So it's a simplicial object in the category of co-commutative, co-unital, co-associative coalgebras. We'll consider a version of the chains functor, which outputs a simplicial co-commutative coalgebra, and consider simplicial sets up to F homology equivalent. This is what this symbol means. A map is an F homology equivalence. A map of simplicial sets is an F homology equivalence if it induces an isomorphism and homology with F coefficient. And Goerss constructed a right adjoint for this change function. Again, this is a right adjoint in the homotopical set. Okay. He constructed this right adjoint by constructing certain model category structures and deriving certain forms. Okay. So he constructed a homotopical adjunction between simplicial sets and simplicial co-commutative coalgebras over an arbitrary field, and proved that if F is an algebraically closed field, such as the algebraic closure of the field with P elements for P of prime, then the unit of this homotopical adjunction is a F homology equivalent. Okay. So you can recover your space or your simplicial sets up to F homology equivalence completely from its F chains considered as a simplicial co-commutative coalgebra. In other words, this functor of simplicial chains embeds fully faithfully the homotopy theory of simplicial sets up to F homology inside this more algebraic, or I should say co-algebraic homotopy theory. The full and faithful embedding of homotopy. That was Goerss' work in '95. And some more history, Mike Mandell considered another version of this problem. Now, instead of using simplicial coalgebras of chains, using DG algebras equipped with additional structure, that of an E infinity structure. So Mandell proved a similar statement as Goerss in a dual setting, working with algebras instead of coalgebras, and working with DG objects, which are commutative up to higher homotopy. Okay. And furthermore, Mandell also considered the integral version of the problem. And he proved that for simply connected finite type spaces, the DG algebra of integral cochains, considered as an E-infinity algebra, completely detects its homotopy type. So, given two spaces, they are weak homotopy with these hypotheses. Two spaces with those hypotheses are weak homotopy equivalent if and only if their E-infinity DG algebras of cochains are quasi-isomorphic. So it's a complete invariant in that sense, but it's not a this functor of cochains is not full. And together with Mahmoud Zainalian, a few years ago, we started exploring the possibility of including the fundamental group into this algebraic package in full generality. And this is the observation that I want to stress today. And it's that the coalgebraic structure of the chains on a case, suitably interpreted, and this is where all the technicalities are hidden in this phrase, completely determines the fundamental group of the space. I want to try to convince you of this and use it in constructing an algebraic models for spaces up to a specified notion of equivalence.
Wait, I think it is supposed to be full. It's not supposed to be onto an object, right? I mean, they have like non-connected infinity algebras, like between the algebras. Oh, maybe I guess I didn't set it up. Like he needs to take like something like this to do it over a
Complete.
Yeah.
Exactly.
Okay.
Yeah, you say that.
Okay.
Or local objects or complete objects over equity. Anyway, I want to convince you of this statement and explain how we can use it, how we can incorporate it into an algebraic package modeling spaces. Okay, yep.
Can I say how different is the DPA compared to the E-infinity?
Yeah, over the rationals, these over characteristic zero, these categories, these homotopic theories are equivalent.
Over
Not, yeah, over characteristic zero.
Yeah.
Over a field of characteristic zero. Over characteristic p, there's obstruction.
over the
Over C as well, yeah. They're not equivalent.
but over the integral they are not.
They're not, yeah.
So CDG is fully faithful in E-infinity. That's correct.
A CDGA, what did you,
The CDG maps to E-infinity.
not,
And this fully
it
faithful.
depends on your coefficient.
So for integer coefficient.
No. So let's try to make sense of this poetic statement. And of course, the chains of the space determines not only a fundamental group, but much more. This might sound surprising at first.
So you have no assumptions on the space.
No assumptions on this space. That's a
That's why.
usual reactor.
So like you take something like B, GL, and
No, I mean-
so if you take those chains, they don't determine. They
They-
don't tell the plasma function.
So you have to say chains as what, and under what notion of weak equivalence. We'll see. So let me start discussing the functor of chains that I will be considering. So let's fix a commutative ring R with unit associated to any set, any bare set. We can linearize that set and define a commutative coproduct on the free R module generated by that set. You just declared that the coproduct to be the diagonal on the generator, right? So associated to any set, one can construct a co-commutative, co-unital coalgebra. And that's a left adjoint. It has a right adjoint called the functor of points. So let's recall these definitions. So if X is any set, I can take all R linear combinations generated by that set, the free R module, and I can declare the coproduct to be the diagonal map on all the elements of the set. And this epsilon is the co-unit. So the co-unit is a map from the coalgebra to the underlying ring, and I can define that to be one on the generator question. And this right adjoint P is explicitly given by the so-called in the context of Hopf algebras. This is a group-like elements function, but in this context, it will not form a group; it will only form a set. So maybe you can call it a set-like element, or also called the functor of points. So given a coalgebra C with coproduct delta and co-unit epsilon, you can consider the set of all elements in which the coproduct acts as the diagonal, and in which the co-unit sends that to the unit of the underlying ring. That's a functorial construct. And the claim is that this functor is full and fade. In other words, I can recover X up to isomorphism completely from this co-commutative coalgebra with some hypothesis on R, namely that the ring does not contain any non-trivial idempotent. That's an exercise.
The whole paper?
What? It's an exercise.
One,
actually. It's a good exercise. We usually learn this in the theory of Hopf algebras over a field, usually. But then if you look at the proof, you see what hypothesis you use. And you use this true for any integral domain, but even more precisely for any ring with known and trivial idempotent. And passing to simplicial objects, this adjunction can be promoted as an adjunction between simplicial sets and simplicial co-commutative coalgebra. You just apply level one, right? And the same claim holds. This functor of chain is as a one category, no homotopy theory here, is full and fade. Under these hypotheses on we will also consider a normalized chains functor together with the Alexander-Whitney natural transformation. So this produces a functor that takes any simplicial coalgebra and outputs a differential graded co-associative coalgebra, which might not be co-commutative, even if you started with a co-commutative coalgebra. If this Alexander-Whitney natural transformation you use to break the coproduct is not strictly co-commutative. Of course, it is co-commutative of the higher homotopy. So you could put here E infinity differential graded coalgebra if you wish, but I will not use this fact. I just want to consider this way of associating differential graded co-associative coalgebra to any simplicial co-commutative coalgebra. And this functor restricts to connected objects. Connected means that in the simplicial world, that at level 0, your coalgebra is just the underlying ring with the usual coproduct. And in the VG world means that at degree 0, the same holds. The coalgebra is the underlying ring with a coproduct that sends 1 to 1 to 1. Right. Okay. That's a notation I will use. This is mainly to introduce notation. Okay, and so there were some people that were skeptical about my first claim, and that's the right attitude. But now I want to introduce the notion of equivalence that will be used to consider coalgebras in order to capture the fundamental group in complete generality. And that notion of equivalence comes from Koszul duality theory between algebras and coalgebras. It's created by the so-called Kovar construct. So I will define by this bold omega the composition of two functors. First, the normalized. First, I'm gonna start with simplicial co-commutative coalgebras that are connected. Applying the normalized change functor produces a differential graded connected coalgebra, and for differential graded coalgebras that are connected, or more generally co-augmented, I have a Kovar functor that produces a differential graded algebra. So what do I mean by Kovar? So this construction was introduced by Adams in 1956. So the Kovar construction, or the Kovar functor, takes as an input a co-associative differential graded coalgebra. So C, this is the differential, this is the co-product, assumed to be co-associative, and this is a co-augmentation. That's part of the initial data, which in our sense is just an isomorphism, because I'm assuming C is connected. It's an isomorphism onto the 0th degree part, right? So the Kovar construction is a free algebra, a free graded algebra with a differential defined in terms of the underlying differential of the coalgebra and its coproduct. Okay, so let me explain this notation. What does C bar means? So C bar means the following. You first look at C and you take the co-kernel of the co-augmentation. In our case, this is essentially healing the degree 0 part of your coalgebra, because we're working with connected coalgebra. And then you shift everything down by 1. If something wasn't degree 1, it becomes of degree 0. Something wasn't degree 2, it becomes of degree 1. And that's C bar. Okay. And now you take the tensor algebra on this R module. That means you take the direct sum of tensor powers of C bar. You take non-commutative monomials in generated by this R module, right? And then you extend the sum of the underlying differential and the coproduct as a derivation to this free algebra. Freely, this is a free algebra, so you can extend the map as a derivation. And then the fact that this squares to 0 is equivalent to this, the underlying differential squaring to 0, the coproduct being co-associative, and the differential and coproduct being compatible. In a differential graded coalgebra, the coproduct is a co-derivation of the differential. So that's the Kovar construct. It was used by Adams to obtain a chain model for the base loop space of a space in the simply connected setting. We will get back to this point in a second. But first, a warning, which is related to why you should be skeptical of many of these constructions. And the warning is that, as I defined it, this Kovar construction does not preserve quasi-isomorphism. It does not send quasi-isomorphisms of coalgebras to quasi-isomorphisms of algebra. So I know there's some homotopy theorists in the audience, and there's a discrepancy in how some homotopy theorists define the Kovar construction and in how I'm defining the Kovar. For example, the Kovar construction, as you find in homotopy theory and in stable homotopy theory and so on, you usually define it as the totalization of a cosimplicial object. It's usually a right adjoint in that context. In this context, this is not a totalization of a cosimplicial object. If it was, you would see a direct product here instead of direct sum. Okay, so this is not a homotopical construction with respect to underlying quasi-isomorphism. See, I'm treating coalgebras as a one category, considering this functor, and now I'm using this functor to create a notion of weak equivalence on this underlying category. Namely, I define a map of simplicial co-commutative coalgebras to be a co-bar quasi-isomorphism if it induces a quasi-isomorphism of differential graded algebras upon applying the co-bar function. See? This is the notion of weak equivalence that I will be using to construct the homotopy theory on coalgebras. This is the notion of equivalence you encounter in differential graded Koszul duality theory, which comes in many different flavors, with algebras and coalgebra with many different properties and structure. Right? There's many versions of this Koszul duality. In other words, there's a functor going back. If I assume in this context an augmentation on the side of the algebra, there's a functor going back, a bar construct, which is a right adjoint, this co-bar. And those functors under suitable hypothesis define an equivalence of homotopy theories when coalgebras are equipped with this notion of weak equivalence, created by the co-bar function. So what's the topological or geometric meaning of this homotopy theory or this construction? Well, it's given. Well, before I say that, let me relate this construction to another construction in the literature. And that's the differential graded nerve functor. It's a version of the nerve functor that takes into account higher homotopy. So the statement is the following. This composition of functors, if I start with a simplicial set with a single vertex, a reduced simplicial set, I can apply the simplicial coalgebra of chains functor, followed by this co-bar functor. This is exactly on the nose isomorphic to the left adjoint of the differential graded nerve functor, which was maybe defined by Goerss, I guess. Restricted to the one object case. So the differential graded nerve functor is a homotopy coherent version of the nerve that takes a category, but now enriched over chain complexes. That's called the DG category, and produces a simplicial set. A DG category with one object is a DG algebra. This nerve functor, when restricted to DG categories with one object, produces a simplicial set with one vertex. This construction is a right adjoint. The left adjoint is exactly on the nose. Again, it agrees with the combinatorics of this construction. Is exactly this composition of functors. Chains followed by the co-bar construction.
Would you get like if you plug in BG for G non-empty?
If you plug in BG here, well, you get I'll make that statement. You get the things on the base loop space on any space you plug, assuming your space is fibrant, your simplicial set is fibrant. I'll make this into a statement in a second. Yeah. So note that this construction is the same as applying the BG Kovar construction to the normalized chains on the simplicial set X. This follows by definition, where you're considering this chains as a differential graded coalgebra equipped with the Alexander-Whitney diagonal approximation. So to answer the question that was asked, it's given by this theorem. If X is a concomplex, is a fibrant simplicial set. If, in other words, if the one simplices of X have inverses up to homotopy, then there is a natural quasi-isomorphism of differential graded algebras from this construction, which was the Kovar construction applied to the coalgebra of chains, and the singular chains on the base loop space of the geometric realization of X. I should say this Moore's model for the base loop space. So it's a model for the base loop space in which concatenation is an associative product, right? So we can construct an explicit geometric map that induces an isomorphism in homology and preserves the algebra structure. Furthermore, we can construct a coproduct on this differential graded algebra, making it into a differential graded bialgebra, such that this map, theta, is a quasi-isomorphism that preserves the bialgebra structure.
Here somewhere these chains iterated integrals.
No, because chance iterated integrals is used. This is pre-Chen iterated integrals. Chen uses this under proof in the proof of the statement. The idea is you can never dualize. Chen iterated integrals is a construction applied to the differential forms, but once you dualize differential forms it's a cohomological model for your space. You have to say consider under what notion of equivalence. But if you're considered under quasi-isomorphism, you lose the information of the fundamentals, right? You only recover this mouse of completion or whatever. But I don't want to do that. I always want to work with coalgebras equipped under this notion of equivalence obtained from Koszul duality theory, from the Kovar construction. This extends the theorem of Adams from 1956, where essentially the same statement was proven, assuming the space was simply connected. So essentially the same statement as Adams is true for non-simply connected space. But the subtlety is the notion of weak equivalence under which you're considering the chains on the underlying space. Adams' construction was working in the simply connected case, and in that case, the Kovar construction does preserve quasi-isomorphism. If you're allowed to consider things that are non-trivial in degree 1, then the Kovar construction will not preserve quasi-isomorphism. And this is related to the failure of convergence of certain spectral sequences. In any case, the same proof as Adams does not go through. We had to use a different argument and be very careful. Okay. It's a space level argument, actually. We formulated this at the space level. In other words, this lambda x, which was the Kovar construction of the chains, can be described as taking the cellular chains of certain cellular model for the base loop space. And we proved that this cellular model is weak homotopy equivalence to the base loop space through a classical compared to quasi-fibrations argument. And then upon applying chains, you obtain this statement. Furthermore, this is a statement that is also not too deep, but it wakes you up when you hear it. A map between two complexes is a weak homotopy equivalence if and only if the map at the level of chains is a weak equivalence. So this is sort of a Whitehead type statement. There's this statement of Whitehead, right? That a map between simply connected spaces is a weak homotopy equivalence if and only if it's a homology equivalence. If and only if it's a quasi-isomorphism at the level. And now I'm working with non-simply connected space and changing the notion of equivalence for coalgebras. And what this is doing is that this is capturing isomorphism on fundamental groups and isomorphism on homology with coefficients in any local system. When you unravel this. See? And now, what if your simplicial set is not vibrant? There was this hypothesis here. This is not true for an arbitrary simplicial set. What if it's not vibrant? Can we algebraically describe a construction that out of the chains produces the fundamental? The answer is yes, still. So the construction is the following. So if X is an arbitrary reduced simplicial set, reduced means it just has a one vertex. The homotopy theory of connected pointed spaces can be modeled in terms of simplicial sets with one vertex. So this construction might not model the DG algebra of chains on the base loop space. So how do we deal with this? We define a localized version of the Kovar called this omega hat. So it takes a simplicial commutative coalgebra, produces a DG algebra as follows. If C is a simplicial commutative coalgebra, this new DG algebra is obtained by first looking at the DG algebra obtained by applying the Kovar function. And then you look at, so C is a simplicial coalgebra. In degree 1 is a coalgebra. You look at the points of degree 1, the group-like elements. That's a set. You formally invert that set. It's a set of cycles. You can see that by definition, the differential in those will always be 0. Remember, we shift everything down by 1, so this will be in degree 0, and the algebra is non-negatively graded. So you formally invert that set. And now you make another definition. A map of simplicial coalgebras is a Kovar hat quasi-isomorphism. If it becomes a quasi-isomorphism of DG algebras upon applying this new Kovar hat construction. I'm doing this to remove this vibrant hypothesis that I had in my previous year. And now what's the statement? For any reduced simplicial set, this differential graded algebra, so you take the simplicial coalgebra of chains, take the Kovar construction, and formally invert the one-dimensional points. This is a differential graded algebra that has a natural extension to a differential graded Hopf algebra. You can construct a coproduct to make to produce a DG algebra structure extending the algebra structure. Moreover, that you obtain a bialgebra. This is part of the statement. And that bialgebra has the property of being Hopf. That means it admits an antipode map. Okay. That DG Hopf algebra is quasi-isomorphic as a DG bialgebra to the singular chains on the base loop. This is always a DG bialgebra. It's not quite a Hopf algebra because running a loop on the opposite direction is only homotopic to the identity, not equal to the identity. Right? But it's still a DG bialgebra. So this is a Hopf model, DG Hopf model for this DG by algebra. And this is the statement I wanted to make. The fundamental group can be completely determined from the algebraic structure of the chain. In this sense, if you apply the simplicial co-commutative coalgebra of change functor, followed by this localized version of the Kovar functor, this produces a Hopf algebra, a DG Hopf algebra. I can take the group-like elements of that DG Hopf algebra. I'm missing a zeros homology here. I'm sorry. Let me write it here. This is what I meant. You take the chains. You take this localized version of the Kovar construction that formally inverts certain elements in degree 1. You take the zeroth homology of that. This is the base loop space, the chains on the base loop space. This is the zeroth homology on the base loop space as a Hopf algebra. And now you take group-like elements, which I'm going to call P. This is isomorphic to the fundamental group.
Does P stands for primitive?
No. Important. Group-like element. Is that clear, the difference? This is different from the primitive element construction and rational homotopy. If you want to obtain the full rational homotopy type plus the fundamental group, you apply this here, and then primitives at the level of universal cover. But this is not primitives. It's a bad notation. This is group-like elements form. Now, if you have a Hopf algebra, there are two things you can do. You can take primitives and get a Lie algebra, or you can take group-like elements and get a group. I'm taking the group-like elements function. The same P I was using here earlier for simplicial coalgebra. In that case, it produced a set, but it's all elements in which the coproduct is diagonal-like. It's a diagonal. Okay.
Yes, so you can localize that character, this category, right? You can take these equivalences. So what's the right category if you do that?
Say that again.
So if you can take spaces and you take these equivalences that you produce from this. So is it rational? And
Yeah.
plus pi one. So what is the derived category of this?
You get, well, first, I'm gonna make a statement about this, but you obtain spaces under the following notion of equivalence. If you work out under the rationals, a map is an equivalence if it induces an isomorphism on the fundamental group, and if it induces a rational homology equivalence at the level of universal cover. That's the notion of equivalence.
Or what is this category?
I'm gonna make a statement that there's a model structure, for instance. You can work over FP. There's also a model structure over FP. So it's a, yeah. So in summary, we have three notions of weak equivalence for coalgebras that I've discussed. For simplicial co-commutative coalgebra, let's say. So I mean, also doing this to introduce this ugly notation that I don't. It's the math bracket thing. Yeah. Anyway, there's a class of morphisms, right? So a map G is in this class of morphisms, quasi-isomorphism, if it's a quasi-isomorphism. But induces a quasi-isomorphism after applying normalized chain function. A map is a Kovar hat quasi-isomorphism if it induces a quasi-isomorphism of DG algebras after applying the Kovar functor and localizing at the degree 1 point. And I also mentioned this without localizing, right? A map between coalgebras is a Kovar quasi-isomorphism if it becomes a quasi-isomorphism after applying this Kovar function. Those are the three notions of weak equivalence. Under suitable hypothesis, for instance, you can forget about these hypotheses if you're working over a field. You have these strict inclusion. So every Kovar quasi-isomorphism is a localized quasi-isomorphism. Namely, this localization procedure is well-behaved homotopy. This has to do with the fact that the Kovar construction would produce a cofibrin Nietzsche algebra. Those are just words. And also any covariant hat quasi-isomorphism is a quasi-isomorphism. So Goerss, Kriz, in their p-adic homotopy theory, we're working at this level. Right? So now you can try to consider deeper homotopy theories for which this one becomes a Bousfield localization. Right? So this is the deepest level. So those are the three notions of weak equivalences for coalgebras. Now let's consider the corresponding three notions for simplicial sets. Reduced simplicial sets. Okay. So let's define a map of reduced simplicial sets, simplicial sets with one vertex, to be in the class of R equivalences if it induces an isomorphism on R homology. And now this is the notion I was just defining. We call pi1 R equivalences the following class of maps. It's a map F of simplicial sets that induces an isomorphism on fundamental group, and it induces a homology equivalence at the level of universal covers. I'm working with reduced objects, so there's a canonical base point for the fundamental group and to construct the universal cover. So these constructions are functorial. The fundamental group and the universal cover. This category. So that's the second notion of weak equivalence. Exercise, if R is the ring of integers, this is the same as weak homotopy equivalence. See that? Use Whitehead's theorem on the universal covers. Right? Third notion of weak equivalence, the deepest one, I'm going to call it R categorical equivalence. Again, these are maps of simplicial sets that induce a quasi-isomorphism of differential graded algebras after applying this left adjoint of the differential graded nerve function. Remember, the differential graded nerve takes a category enriched over chain complexes and produces a simplicial set. But if that category has one object, that's the same as a differential graded algebra and produces a simplicial set with one vertex. So you have three notions of equivalence on the category of simplicial sets. And you can try to relate them to the previous three notions of equivalence on simplicial coalgebra. And let me just make a statement with words. The statement is the following. Maybe this is not a good idea, but let me just say it. Just put it in my slide. You also have these strict inclusions for these notions. These are also exercises, right? Any R categorical equivalence is a pi1 R equivalence. How should you think of this? R categorical equivalence is a type of linearized quasi-categorical equivalence. Now, simplicial sets form a framework for both homotopy types and infinity categories. Now I'm linearizing your infinity category. This is the notion of equivalence you get is this R categorical equivalence. So this inclusion is sort of analogous to saying that categorical equivalences are weak homotopy equivalents, but not vice versa. Right? These are stronger. And this is analog to saying weak homotopy equivalences are homology equivalent, but not vice versa. You have this sequence of strict inclusion. So you can consider simplicial sets under these three groups of weak equivalence. So here are the main statements that I want to make. The first statement, you don't need any fancy abstract homotopy theory. The first statement is that the functor of simplicial chains that takes a simplicial set and produces a simplicial co-commutative coalgebra reflect each of these three pairs of notions of equivalence. Namely, a map is a weak equivalence in simplicial sets if and only if it's a weak equivalence at the level of coalgebras after you push it with this function. If and only if, for these three pairs of weak equivalent. We sort of discussed this already. The first one is at extreme tautology, right? Like a method is like isomorphism, if and only if an isomorphism of homology. The definition is tautology. The second ones have a little bit more context. So, is that clear? It reflects these notions of weak equivalence. The next statement will be a statement about abstract homotopy theory for each pair of notions of weak equivalence. Note that this is true over any commutative ring R. For the next statement, which we proved recently with George Raptis, I have to assume F is a field, but it's a field of arbitrary characteristics. So the interesting statement here is when F is FP, right? So for each pair of notions of weak equivalence on simplicial sets and simplicial co-commutative coalgebras, the simplicial chains functor, this is an F, I'm sorry, this is also an F, that's a typo, has a homotopical right adjoint P deriving the functor of points. That's the first thing. It's a weird way of saying it. I just didn't want to use the words, say, model category. But the statement is that we construct model category structures on both categories for each of the three nodes. And this allows us to consider a derived functor of points. And, or maybe before saying that, I should have said that with those three different homotopy theories, the adjunction between chains and points becomes equivalent adjunction. That's a statement. I'm just saying it in this way. And when F is an algebraically closed field, such as the algebraic closure of Fp, the unit map or the derived unit of this adjunction is a weak equivalence in all three cases. In other words, in the three contexts we have discussed, the functor of chains from simplicial sets to simplicial co-commutative coalgebra is homotopically full and faithful in the three contexts. The deepest context, which was these Kovar quasi-isomorphisms, is the one that you apply all the work there, and then you have these Bousfield localization machinery that you can Bousfield localize to get the other two weaker homotopy theories. So you can recover X up to weak equivalence from its chains, where the word weak equivalence can be interpreted in these three. From its coalgebra, simplicial coalgebra. That's the statement. Yeah.
So is the right adjoint P the same for the three type of models?
It's the same. The same functor of one category. But you have three different homotopies. So when you derive that functor, you obtain different functors. You derive it with respect to three different notions of weak equivalence. Let me just quickly mention the key ingredients in the proof of this statement. So, as we have said, this uses the homotopical meaning of the Kovar construction as a model for the chains on the base loop space. As I also said in Goerss, we construct three model category structures on reduced simplicial sets and on the side of simplicial co-commutative coalgebra. One corresponding to another one, so three pairs, such that this becomes equivalent adjunction in all three cases. This uses transfer of model structure techniques, Bousfield localization, and some abstract nonsense. Right? The key idea is how the Kovar construction captures the fundamental group, which I explained. That's the key idea. The rest is just abstract nonsense, as I said. And there's also in the statement about F being algebraically closed and being able to or that the chains is full and faithful in this case, that makes use of the structure theory of co-commutative coalgebras over a field. This I learned from Paul Goerss, but I think it goes back to Sweetler. It's essentially a dual of the Nullstellenstadt. That's the statement that's being used in some sense. The precise statement that I mean here is the following. If F is an algebraically closed field and C is a co-commutative coalgebra, this is not simplicial, it's a co-commutative coalgebra over F, then the inclusion from the, you can take the points of C and then take this free coalgebra generated by those points, not free coalgebra, free vector space with the diagonal coproduct. That admits a natural retraction of coalgebra. There's a splitting, and which is natural if F is algebraically closed. That's the key statement that's used in the proof that in this case the chain functor is full and faithful in all two things. I can explain how this is used if there's interest later. How to come from here to the fact that the chain is full and faithful using what I've just said. Not hard. Finally, we also proved a stronger statement or an arbitrary perfect field. So if F is a perfect field with absolute Galois group G, then we can say the following about the derived unit of our adjunct. For any reduced simplicial set, this derived unit in each of the three contexts may be naturally identified up to weak equivalence with the following map. With the map from X to the homotopy G fixed points on X considered as a simplicial set with the trivial G-equivariant. So this has three different meanings depending on your notion of weak equivalence, right? The homotopy fixed point. To make sense of homotopy, we use a covalent replacement and so on, but that depends on the notion of weak equivalence. So for each of these contexts, the derived unit can be identified with the map from X to homotopy fixed. And that's the best statement we can prove for a perfect field. And maybe to end, let me mention some work in progress. So this, I'm sure it's true, but it's surprisingly tricky to prove. One should be able to deduce the following integral statement. If X and Y are simplicial sets, then they are weak homotopy equivalent, no hypothesis. If and only if their co-commutative integral coalgebras are Kovar quasi-isomorphic. I am able to prove this under the hypothesis when the universal cover is of finite type, applying Mandell's theory and so on. But it's surprisingly tricky to paste all the statements that I obtain over FP to obtain this integral state. I mean, philosophically, we know it's true for all P and so on, and for the rationals, but it should be true over the integers. But there's some gluing data and some theory of coalgebras that I failed to get my head around it. But maybe with enough time and help, I can prove it. Then the next question is, how about obtaining a full and faithful model for homotopy type instead of this? You would have to consider coalgebras with more structure. Just considering, for instance, E-infinity coalgebras under this notion of weak equivalence, or simplicial co-commutative coalgebras will only give you a faithful model over the integers, possibly, but not full. So probably if you consider coalgebras with more structure, you can get homotopy types completely in terms of coalgebraic objects. Linearized objects equipped with nonlinear structure. And second, my student, Sophia Martinez, who will be coming here tomorrow, is studying G-equivariant versions of these statements using a framework developed by Stefan, which is itself inspired by classical results of Elmendorf, of promoting certain homotopy theories to the G-equivariant concept. And I think I'm out of time and I'll stop.